Tonight, I'd like to offer you a choice. To get to your destination, there's the long way. It's going to be rather laborious, repetitive, take you a long time, might even be a few dangers on the way that will kind of waylay you, might not actually even get to the destination because of the dangers that there are. But there is a second way that I'm going to offer you. And that's the shortcut, a sign saying to go off to the side, seemingly going in the wrong direction maybe to start with. But I'm going to promise you some exciting journeys on this way, some interesting views, and the promise to get you to your destination quickly and more efficiently than the long way. And to help you, I've written a new book, Thinking Better, The Art of the Shortcut, which gathers together a whole suite of exciting ways of thinking cleverly about problems so you don't have to do the boring, long, laborious work that the other people are doing. I actually learned about my first shortcut when I was about 12 or 13 at my school. The mathematics teacher told us a story, a very famous story now, about the young Carl Friedrich Gauss. Any mathematicians out there will know probably the story that I'm going to tell you. The mathematics teacher in Carl Friedrich Gauss's class challenged the students with a problem. He said, I want you to add up the numbers from 1 to 100. I think the teacher thought that this would take the students so long that he'd be able to get a little bit of a rest. And sure enough, the students started adding 1 plus 2 plus 3. It was going to take them a long time. However, the young Carl Friedrich Gauss, even before the teacher had finished posing the problem, had written down the answer on his slate board and slammed it down in front of the teacher. The teacher thought he was being impudent, but when he looked at the slate board, there was the correct answer, 5,050. And the teacher said, well, how did you get that so quickly? Did you cheat or something? He said, no, there's a shortcut. See, all my fellow students are starting at the beginning of this journey and just plodding through the numbers one after another. It's going to take them ages before they get all the way to 100, and I'm sure they're going to make some mistakes on the way. But I took a step backwards and I realized you can combine the beginning and the end of the journey. You can add 1 plus 100, and that gives you 101. 2 plus 99 also gives you 101. 3 plus 98, 101. So he realized that there are 50 pairs of numbers all adding up to 101. So the answer was 50 times 101, 5,050. Now, what I love about this shortcut is that even if the teacher had said, okay, I'm going to make it really difficult for you, young Carl Friedrich. I'm going to ask you to count the numbers from 1 to 1,000,000. He could still use the same trick. Once he dug that tunnel, understood the kind of shortcut to understanding this problem, it worked really however large the numbers were going to be. And for me, this was the moment when I realized the subject I wanted to dedicate myself to, because my mathematics teacher said, this is what our subject is about. Mathematics, it is the art of the shortcut. And what I'm going to do over the next few years is to teach you the extraordinary shortcuts that we mathematicians have come up with over the last 2,000 years. And being a lazy teenager, I said, oh, wow, that is the subject I want to dedicate myself to. So my dream began to become a mathematician. And it's interesting, I'm not trying to give the impression that these shortcuts are going to stop us doing any work, because actually, as a mathematician, I quite enjoy the work I do. But it's important to me that I can choose the work I want to do. So it's interesting that Aristotle already had identified 2 different sorts of work. Praxis, work for its own sake, the work that you kind of enjoy doing. And then poiesis, the work just for the goal, for the outcome. You just want to get to the end. You don't really mind how you get there. And if there are shortcuts to get you to that goal, you're going to take them. So the shortcuts I want to offer you to tonight and that are in my book are shortcuts to stop you having to spend all your time doing the work for its outcome, the poiesis, so you can get to the work you really love doing, the praxis. And in a way, this was Karl Marx's ideal for communism. He always said, in a higher phase of communist society, labor has become not only a means of life, but life's prime want. So my hope is my shortcuts are going to help you to do the things you want to spend your life doing. And Carl Friedrich Gauss actually is a companion throughout my journey of these shortcuts. His biography, somehow he seems to be involved in many of the shortcuts I talk about in the book. So he starts the journey of the book at the tender age of 8 and 9 in the classroom. But I found that he had a part to play in many of the shortcuts that I'm going to talk about. So I'm going to give you a little bit of a tour of a few of the shortcuts we can take on the way to our destination. And it's interesting that actually nature has been taking shortcuts for a long time before mathematicians started to find them. And I think nature, a bit like my lazy teenage self, is itself lazy and loves finding clever ways to get to solutions. So the first shortcuts I'm going to talk about, we sort of discovered that nature is doing them. So for example, the honeybee. Why does it make its hive out of hexagons? Well, this is actually a shortcut because we've discovered now, mathematicians have proved that the hexagons are actually the shapes that when you put them together, use the least amount of wax in order to make shapes which will contain a particular volume of honey. If you make squares, or triangles, for example, which are also perhaps an obvious lattice, you actually use more wax. And for a honeybee, actually making wax is expensive. It's hard work. So it wants to find a low energy solution, an efficient way of making the hive such it can contain the honey, but use as little wax as possible. So nature found this incredible shortcut to using as least wax as possible. Bubbles as well. Interesting, when you blow a bubble and it wobbles around, but eventually it forms this beautiful spherical shape. Why does it form a sphere? Because again, nature is looking for the low energy shape. Just as the same way as if you put a ball on the top of a hill, it will roll down into the valley, the low energy place. A sphere turns out to be the shape which uses the least amount of energy to contain that volume of air. So the surface area of the bubble is proportional to the energy needed, and the sphere is this shape with the smallest surface area. And so if you form interesting shapes like this frame here and put a bubble over it, what the bubble does, nature finds the most efficient way, the low energy state, to fill the frame with that film. And humans have taken advantage of this. If you've ever been to Munich and gone to the Olympic Stadium there, a really beautiful building, very kind of organic looking. And Fry Otto, who built the Munich Olympics, used the idea that bubbles will find you the low energy solutions to how to put a canopy on a frame to be able to choose the designs for the Munich Olympic building. And so these are actually large-scale versions of the bubbles that he made on the small frames that he made in his studio. And because they are low energy, it meant that there wasn't too much stress on the material that was put on top of this frame. And so in science, we actually have this idea that nature is lazy. In everything, nature is thrifty, once said Maupertuis. The idea that nature seems to want to find the solutions, the most efficient way of getting to the solution. A very interesting example of this is actually light. Light always tries to find the fastest way to get from its source to its destination. So this is what causes this strange effect that if you're in a swimming pool, your legs seem to be very short. In fact, if you put a ruler in, you suddenly see the ruler is bending. That's because the light realizes that the speed it can go in the water is slower than in the air. So it tries to get out of the water quicker so it can speed along in the air and gets to its destination as quickly as possible. Now, it's kind of curious, how on earth does light do this? Because how does it know where it's going? And it seems that it's exploiting quantum physics in order to be able to try out all the different paths, but it collapses into the path which is the quickest way through the water and the air. But what about us humans if we are challenged with a similar sort of problem? So here's a problem where a lifeguard has to go and rescue somebody out at sea, but the lifeguard can run faster on the sand than he can swim in the sea. So what's the optimal point to choose to be able to get to the drowning swimmer as quickly as possible? Well, if you can run faster on the sand, then maybe you want to just run sort of to the perpendicular point from the swimmer, but then actually you'll be wasting a little bit too much time. So there is a sweet spot, a point where the light would equally find its way through these two different mediums, the two different speeds it goes. But how do we humans find that sweet spot? Well, we've come up with a clever shortcut, which is the calculus. I would say one of the greatest shortcuts humans have come up with, which enables you to take a situation where there are multiple scenarios, and the calculus enables you to focus in and find the solution which maximizes or minimizes whatever it is you're trying to look at. So this tool of the calculus has been incredibly important, for example, in understanding in economics how to maximize profits. But in this case, it would also be able to tell you that point at which you will get to the swimmer the quickest way possible. And of course, this shortcut was created by Newton and Leibniz, and they actually used it to solve a very curious problem at the time, which was perplexing the mathematicians, which was if you've got a ball and you want to create, say, a roller coaster ride where the ball or the train has got to get as fast down as possible from the top through to the station at the bottom, what is the curve that will get you the quickest using gravity from the top to this point at the station at the bottom? Maybe it's just a straight line which goes from one point to the other, or perhaps a quadratic equation which sort of comes and levels out at the station. But it turned out when they applied the calculus to this and looked at all the different possible curves, what was the curve that would get you quickest from A to B? It was a very curious curve, a curve which perhaps you wouldn't have found without this shortcut of the calculus. And it turns out actually the curve you need to go down below the station and use the gravity and the speed that you've built up to shoot back up to the destination. And the curve you need is something called a cycloid. So what you need to do is to take a bicycle wheel and you put a pen at the bottom of the bicycle wheel, and then you wheel the bicycle wheel along, and the curve that the pen marks out is this thing called a cycloid, and then you want to turn this upside down, and this is the curve which gets your roller coaster fastest from the point at the top to the station at the bottom. So differential calculus is an extraordinarily amazing shortcut. So you can look at a scenario and work out what the most efficient way is to get to your destination without having to try all the different possibilities out, like it seems perhaps quantum physics is using to find the light to its destination. So that, I would say, is one of our greatest shortcuts. But what about our modern age? We're being kind of bombarded with so much amounts of data. We're leaving so much data around us. How can people pick up signals and information from this data? Are there ways to take data and in this enormous mass of numbers find shortcuts to find the secret information that's inside there? Well, yes, there are, and this is one of the shortcuts I learned at university, the idea of a statistical sample. When is that good enough to be able to tell you a lot about a large sample? And there was always an advert which I used to watch as a kid, which I found very curious, and it took me some time to understand that there was a shortcut hiding behind this advert. It was for cat food. Some of you might remember this, Whiskas cat food. And the advert very boldly claims that 8 out of 10 cats preferred this type of cat food. Now, this is very curious to me because we had a cat at home, and I do not remember anybody coming and asking my cat what sort of cat food it liked. So I was curious how they can make such a bold claim. And it took to get to university to find out that there's something like 7 million cats in the UK. I mean, how many cats would you need to ask? You don't have to ask them all. That's fair enough. So maybe our cat was just unlucky not to be asked. But how many cats would you need to be asked to give you a really good sense that you can say something as bold as, 8 out of 10 in the large sample, the 7 million, will seem to be preferring whiskers. So that's the kind of challenge. You've got this large population, 7 million. What sort of number do I need to take to be confident about a claim in the larger sample? Turns out to be really small. You just need to ask 246 cats. And 19 out of 20 times, this will be within 5% of the true value in the large population. Now, that was staggering to me when I learned that just as few as, just under 250 cats gives you that kind of insight. And for me, this is a very powerful shortcut to be able to know I only need to sample this amount. Of course, you have to be careful here. You have to make sure your sample is truly random. And there have been some very classic examples where the sample has kind of favored a particular part of the population. Very famous one in America very early on when they were doing political polls. They decided they were going to phone everybody up to ask them what they wanted to vote. But at the time, you had to have a lot of money to be able to own a telephone. So they got a very biased selection. So one of the challenges with sampling with a small sample size like this is to make sure that you're sampling truly randomly and independently. Another interesting case where how much data do I need to know in order to be able to make a decision is in one of these classic game shows like Deal or No Deal. So probably everyone knows how you play Deal or No Deal. A number of boxes, each box containing a sum of money, and you gradually select more and more boxes, and at some point you have to make a deal and go with the next box or the box you've got. I'm going to make it slightly more complicated. In Deal or No Deal, you know the different sums of money from $1 to maybe $1 million. In this game, you don't actually know what the values are in the box. So suppose there were, say, 26 boxes. You don't even know what the maximum prize is possible in these boxes. What sort of number of boxes would you have to open up to get a feel for what these prizes are looking like, such you can make some sort of decision about when you're going to opt for, I'm going to keep this box. So this is actually very similar to a dilemma we have quite often in life, where we're not really sure what's out there, and we're going to have to start to make a decision about when we take the plunge. For example, when you're looking for a flat to buy or something, and you go and look at the first flat, and it's wonderful, but you have this one terrible sneaky feeling that maybe there are better flats out there, cheaper flats, or I think the classic one is your partner for life. Your girlfriend or boyfriend from school, just wonderful, but you have this kind of just worrying feeling, but maybe I need to see who else is out there. And so, how much of the scene do you have to sample before you take the plunge and say, yes, this is the one I'm going to marry? So can maths help you as a shortcut to know, how many girlfriends or boyfriends you need to have before you take the plunge, or how many boxes you need to see? Well, yes, indeed, there is a clever shortcut. It involves one of the most famous numbers in mathematics. So probably top of the pops of mathematical numbers is pi, to do with circles, but maybe number 2 in the top numbers is E, this number connected with Euler and natural logarithms, 2.71828, and then goes off to infinity, rather like pi with no patterns to them. But it turns out that this number is also the key to understanding when you should make your mind up and take the plunge. Because if you look at these different sorts of problems, what they all have in common is somehow having to take a proportion of the data. How much do you need to see before you can then try and make the best decision? Turns out you have to consider 1 over E of the population and then make a decision after that point. So 1 over E is about, I think it's about 37%. So you need to see about 37% of the data. So in the case of the boxes on Deal or No Deal, you don't know what's in the boxes, you've got to see 37% of those boxes. And then the strategy is that you must take the next box that beats all of the boxes that you've seen up to that point. Now, clearly this is not going to guarantee you the best box, but 1 in 3 times this will guarantee you the best box. And this turns out to be the best you can do in this particular game scenario. So looking at 1 over E of the proportion of the boxes, choose the one that beats everything you've seen up to that point. 1 out of 3 times, that will get you the biggest prize in all of those boxes. And so the same also applies to your partner for life. So you've got to look at about 37% of the kind of options out there and then go for the one that's beaten all the ones you've seen up to that point. But on your wedding night, please do not show your workings out when you show her or him why you made the decision you did. But there seem to be great shortcuts in understanding in this huge data onslaught that we're having how to understand information hiding inside there. One of the other great shortcuts I love is drawing a picture. A diagram is a very powerful way of capturing the essence of the information that you're trying to understand in a particular problem. Now, there's a danger here, and it's something I should perhaps point out. These shortcuts I'm trying to offer you, they're not about cutting corners. This is about genuinely getting you to your destination. I mean, if you're building a building, you don't want the shortcuts which are going to mean the building's going to fall down in 10 years' time. No, these shortcuts, I really genuinely want you to solve your problem, get to your goal, get to your destination. But in a way, the diagram shortcut has a little element of cutting corners because it's about saying, hey, look, there's information here which is not important. I'm going to throw it away and kind of distill the things which are really important to try and understand how to solve this challenge. I think one of the most exciting diagrams which really changed things politically was, for example, Florence Nightingale's rose diagram, which showed jet deaths during the Crimean War. She was out there trying to tend to the soldiers that were being brought in injured to the hospital. And she was horrified to find that actually most of the people, the soldiers that died, were not dying from the injuries they'd sustained in warfare, but were dying from infectious diseases that they were catching in the hospital, things that could be prevented. And when a sanitation committee came out to the Crimean battlefield and looked at the hospitals, they understood that they were so dirty that this was what was killing the soldiers. And so they cleaned out all of the latrines and sterilized things. And after they'd done that, the drop in the number of casualties because of infectious, of disease and things was dramatic. And Nightingale went back home and wanted to try and persuade government about this new insight that it wasn't war that was killing soldiers, it was bad health. And so she tried to explain to politicians what was going on and people weren't listening to her. And then she decided the only way to do this is to show them a picture in the eye what was going on. And this rose diagram that she produced kind of first sort of kind of pie chart that was created was her way of persuading government. So in this picture, the red and black petals correspond to deaths of soldiers due to warfare, but those large blue petals, those are the ones that correspond to preventable deaths from disease in the hospital. And you can see the moment that the sanitation committee came in, so the kind of all the terrible cases are on your right. And then the sanitation committee came in and suddenly the number of deaths dropped dramatically from February onwards. And this diagram was the one that convinced government eventually that they had to change policy and do something about the sanitation in hospitals. There's a similar story actually that I discovered which is relevant to our particular period of the pandemic. A few years ago, I invited to Oxford to give my annual kind of public science talk, Ian Lipkin, who advises the US government on preparation for pandemics. And he, some years ago, about a decade ago, was trying to persuade the US government that they needed to do something because there was a real palpable threat from pandemics. And so he wrote a 200-page document which he sent to politicians in the US, and this document never got read. And then he realized, okay, It's just far too much data there. He distilled it into a 2-page PDF, which he then sent politicians. Still didn't get read. So he said, what am I going to do? I'll have to take a different approach. And he used a visual approach and a storytelling approach, because he actually then became the advisor on the film Contagion with Matt Damon in. And that film was then sent to politicians, and they suddenly woke up to the importance of preparing. Well, I'm not sure they really did wake up. And Ian actually said to me when he came over, the science was incredibly accurate in this film. And everyone praised the other, and many other scientists praised the science. But the one thing they criticized him for is, well, yeah, it's all great science, but in that film, you got them finding a vaccine within a year. I mean, that's just ridiculous. That would never happen. And so he wrote to me just recently, so I'm very pleased to say that, we've now proved that even that is possible. But it's true. In the past, there didn't seem to be shortcuts to be able to find a vaccine other than trying things out for years and years to be able to. But we do seem to have found some shortcuts, at least for getting us a vaccine within the year. But, you have to be careful with a diagram. The whole point about a diagram is, you don't want all the information there which gets cluttered. So that's the power of a diagram, is deciding what to throw away. But there's a rather nice story that Lewis Carroll once wrote. It's called Sylvie and Bruno Concluded. And in this land that he talks about, they've created this wonderful map of the country. And you think maps are, in some ways as well, fantastic diagrams, shortcuts to navigating your way around a country. But this map, they just couldn't decide what to throw away. They felt everything was quite important. So eventually they said, we actually made a map of the country. It was on a scale of 1 mile to 1 mile. The narrator said, well, have you used it much? Well, it's never been spread out yet. The farmers objected. They said it would cover the whole country and shut out the sunlight. So now we use the country itself as its own map, and I assure you it does nearly as well. So it's important to be able to throw information away, because if you keep all the details, you just can't see what's going on. And I think some of the greatest diagrams we've come up with have enabled us to understand, the very big in our universe and the very small through drawing a picture that we can draw on a piece of paper. So Copernicus's great insight about the idea of a sun-centered solar system. He wrote a very long, hundreds of pages about his idea. But what really convinced people was this little diagram he put at the beginning of the book. And it's not a true diagram representing the solar system. The planets don't do perfect circles. They're not evenly spaced like in his diagram. But it captured the information that he was trying to communicate, the idea of the sun being at the center. And any chemists amongst you will, of course, be drawing these little pictures of molecules with letters and lines joining them. Particle physicists understand the interactions of particles using these wonderful diagrams, the Feynman diagrams. And these truly are a wonderful shortcut, because what they represent are actually very complex mathematical equations, path integrals, which, if you look at the mathematics, very hard to navigate your way through what is possible with these particle interactions. And Feynman himself was struggling with the mathematics and eventually came up with this clever idea of these little Feynman diagrams, which is now the tool that most people will start with in order to understand what a particle might be doing. Actually, a diagram I didn't include here, a very famous diagram, was the double helix structure that Crick and Watson had in their Nature paper. And actually, I've seen a picture of Crick and Watson's first attempt to draw this double helix. And they couldn't resist, rather like that map of the country, putting all the extra details that they found about the molecular makeup of the double helix. And it was cluttered and confusing. And eventually, Francis Crick took this little image that he tried to make back home to his wife, Odile Crick, who was an artist. And she was eventually the one who said, well, what's important about this little picture you've drawn? She was mostly her art was mostly about drawing portraits, but she then helped Francis draw a really beautiful picture of that double helix. And it's actually Odile Crick's diagram, which is the one that was published eventually in the Nature paper. So, the powerful combination of art and science and being able to communicate, shortcut the information and tell you what's going on. But, diagrams can be very dangerous. They can be very, you can use diagrams to confuse and to try and give people information that really isn't there. So some of the classic examples of abuse of diagrams to try and communicate information. For example, take these ones. The diagram on the left was actually the one that Fox News used to try and explain all the tax cuts that Bush had in place. If they get removed, this is going to be the change in your the taxes you're going to be paying. So you see that diagram, it looks terrible. I've got my taxes are going to grow enormous if these tax cuts are taken away. But what was very sneaky about Fox News was, of course, where did they start the graph? At 34%, not at 0. So if you actually put it at 0, what does it look like? It doesn't look that big a change, actually. So, but that's not what they were trying to they were cheating and trying to communicate something different. So always look and see where your graphs are starting, because they might be trying to use that diagram to trick you. Here's another classic one. Company C is trying to show that its profits are so much bigger than its competitors, Company B and Company A. But what they've done, you see, Company A, only $1 million profits. Company B, double that, $2 million. Company C, $5 million. But that's just the height. Of course, what they've done is also bulked out the width. So you need actually 25 copies of Company A to cover what looks like the profits of Company C. So that's another classic abuse of a diagram. So I'm always a little bit nervous of this diagram shortcut because it can kind of lead you astray. I mean, I always like Descartes' sort of idea of sense perceptions are often sense deceptions. So I quite like in my work, trying to change things into kind of algebra as my sort of shortcut. But we live in a very networked world at the moment, trying to navigate lots of different networks out there, friend networks, internet networks, trying to find a way quickly from one place to another. And mathematics has come up with some great shortcuts in order to help us to navigate some of these networks that are out there. And actually, the beginning of our journey into finding clever ways to work our way around networks happened some centuries ago. A very famous problem, I think the challenge of adding up the numbers from 1 to 100 that Gauss was given. I'm not sure if even that story is true, but it's one of our fairy tales that we tell. One of the other mathematical fairy tales we love to tell our students is about the challenge of the Bridges of Königsburg. 18th century citizens in Königsburg used to like to try this Sunday afternoon challenge of trying to cross all the bridges in the city once and once only. Because they had this river Pregel came in with 2 branches, then it formed around an island at the center of the city and then went out in a single branch out to the Baltic Sea. These 7 bridges across the city, was it possible to cross all of the 7 bridges once and once only? But however hard they tried, there always seemed to be one bridge left over. But they were always worried, well, maybe we haven't tried all the different possibilities. So that's the long way, of course. Try all of the different, list them all out, and show that you can't, that none of them achieve the goal. But there is a shortcut, and this is the shortcut that another of the great shortcutters of mathematics, Leonhard Euler, came up with when he was told about the challenge of the Bridges of Königsburg. And in fact, he used our diagram shortcut to find out a clever way to think about this problem. So he said, well, it isn't really important what the geometry of the city is, what the bridges look like or anything like that. What's important is just how the city and the different islands and different sides of the city are joined together. So he replaced this kind of geometric map with a new sort of map that we now call a topological map. So this just reduced all the land masses to single points, And then there were bridges collecting those land masses. They were then lines joining those points. So this idea of topology, drawing a diagram which shows the way things are connected together, of course, some of you may have come tonight to the Royal Institution on the London Underground. Of course, that was a wonderful diagram, a topological map of the way the stations in London are connected together. It's not a geometric map. The distance from Caledonian Road down to King's Cross is much larger than the distance from, say, Piccadilly Circus to Leicester Square, yet on the map they look the same distance. But you don't care about that because you just want to know that there is a route getting you from one to the other. And this was Beck's a great insight when he made this map of the London Underground in the 1930s, which before that map, people were very reluctant to go on the Underground because they just couldn't understand it with this geometric map. But the topological map just laid very clear, became their shortcut to being able to take the Underground wherever they wanted to. So this is a kind of little overground map of Königsberg. But the point is that Euler realized this challenge that they were trying to achieve of crossing all the bridges once and once only is the same as trying to draw this diagram without taking your pen off the paper, but never going over a line twice. So, can you draw this little picture in that way? And so I can see some people shaking their heads, no, you can't. And the reason you can't is that if you're drawing this picture, then in the middle of the journey, if you go into a point on one line, then you have to go out on another line. So it means that most of the points in the map have to have an even number of lines coming in and out of them. Because there are only two places where you can have an odd number. That's at the beginning of the journey, where you start at a point and go out, and perhaps the end of the journey where you then finish on a point. So it turns out that any map where there are more than two places with an odd number of lines coming out of all of the points is going to be impossible to draw. And if you look at this map here, well, every point has an odd number of lines coming out of it. And so this is impossible. Now, I don't think it would have taken too long for the citizens of Königsberg actually to list all of the possible paths around it. It's not that complicated. But what if I had, say, 45 bridges and I drew a whole network of how they were connected together? Then it'd be much more difficult. And there's an interesting example of a place with 45 bridges with different areas of land and the challenge of whether you could walk all of these 45 bridges. And it's actually the city of Bristol. So a mathematician in Bristol drew the map of the 45 bridges and discovered actually this passed Euler's test, that there were only two places which had an odd number of bridges coming out. So he knew that was where he had to start and end. And on one day, he spent 11 hours mapping out the journey he knew that was possible to cross all of the 45 bridges and achieve that possible path. So I think this is a beautiful shortcut that Euler came up with, because it just means you can take as complicated a map as you want, and then you just count the number of lines coming out of each point, and that's going to tell you whether it's possible or not. You do not have to try all the different possibilities. I actually had the chance to go and visit Königsberg and have a look at these bridges a few years ago on a trip I did with the BBC when we were making the series The Story of Maths. The town is no longer called Königsberg. It's now part of Russia. It's a Russian exclave because it's actually a little bit of Russia surrounded by other countries. It's called Kaliningrad now. But modern day Kaliningrad doesn't have all of the old bridges. A few of them still remain, but most of them were bombed during the Second World War by the Allies. But a few have been rebuilt, so there's a dual carriageway which runs through the town and over the islands. There's now a new railway bridge, and you can actually walk across the railway bridge. The BBC team that I went with thought this was such a miserable place, Kaliningrad. They really hated it. But for me, it was like going to mathematical Disneyland. And so I insisted that we spend at least the afternoon considering the 7 bridges of Kaliningrad. And what's wonderful is if you draw the little map, the diagram of how these bridges are connected, the 7 bridges of Kaliningrad it is possible to walk them all once and once only. So we spent an afternoon walking the bridges to prove it's possible, but with Euler's a shortcut, you could know already in advance that you were able to do it. So very nice, now possible to do the 7 bridges. So networks, this idea of how to navigate a network, very important in our modern age. The internet, for example. I think we have this extraordinary tool, Google, for example, to navigate very quickly huge number of websites. If you want to know where to go to, you type in your idea, Gauss biography, and up comes the biography of Gauss. I mean, how does that work? That's amazing. It's not little Google elves at the other end go, "Hey, what's a biography of Gauss?" No, it's an amazing piece of mathematics. Again, a shortcut we teach our undergraduates at university. Something called the eigenvalue of a matrix enables you to find a very fast way to navigate the internet and come up with the places you want to visit. And this was a shortcut that Larry Page and Sergey Brin, when they came up with Google when they were students, had learned about and exploited for the shortcut that we use to navigate the internet. And what about our friendship networks? You might have heard of this thing called the 6 degrees of separation. That if I choose one of you in the audience and perhaps one person randomly watching from Sacramento, could we find a connection between these two people with just friendships, a link of friends? Maybe I've actually narrowed it down, because if anyone who's watching the RI and here at the RI, you've probably got, or we could probably do it in 3 or 2 or something. But what about randomly? If I choose 2 random people in the world, it turns out that our network of friendships have a very strange property that, we seem to be able to always find a way to connect through a friend of a friend of a friend of a friend. It just takes 6 friends to connect 2 people on the planet. Now that's extraordinary. What an amazing network that has that kind of possibility of a shortcut to get from one place to the other. And we call these sort of networks that have this property small world networks. And we've understood what it is about a network that gives it this kind of quality of being able to get from one place to the other in such a short number of steps. And it turns out that your friendship network mostly consists of people that you know around you, your local friends in your neighborhood, your school, your workplace. And then you'll have a few sort of global friends, people you know, maybe in Sacramento or in India. And you just need a few of these long-range connections which join up the local friendship networks to be able to create networks that have this property of being able to move very quickly from one place to another in just 6 moves. So our friendship network seems to have that quality to it. But another very important network that seems to have this small world property are our brains. Here's an example, actually, of one of these small world networks. So, for example, here are, how many are there? 20. 20 friends, for example, each knows the one next to it, but we just join a few together across the whole network, and this will have the property that you can get around it very quickly. So these are what we call small world networks. And as I said, the brain, it turns out, seems to tap into this quality. So we have a lot of local connectivity in the neurons, so they can talk very quickly to things nearby. But we also seem to have quite a few global connections across the brain, which enable the brain then quickly to talk to another part of the brain which might be quite far away from it. And it seems that the way the neurons are connected also have this kind of small world property. This is actually Gauss's brain. Gauss, when he died, decided he would leave his brain to the university in Göttingen where he worked so they could investigate what was so special about his brain that made him such a good mathematician, such a good shortcutter. And it turns out that it does seem to have a rather special quality that it seems to be more kind of folds in it than a normal brain, as if it's trying to make connections that the rest of us have to go kind of the slow way around. Yes, in fact, his brain got mixed up with somebody else's brain for a while, and it was only when they took a scanner to this, and this image had been made kind of when the brain had been donated, and they realized it didn't match up with the brain they got in the museum, and so they had to find one which did look like this one, and so eventually they got put together. But so we found wonderful ways to get around these networks. Now, one of the other qualities of this book is I thought, well, it's kind of celebration of mathematical shortcuts. But I also was quite intrigued to see whether other professions had their own sort of shortcuts that they exploited. And were they ones that I recognized from a mathematical perspective, or were they new ones that I might be able to use in my own field? So part of the book, I take what I've called pit stops between the shortcuts, and went and talked to lots of people in different professions about whether they had shortcuts, or perhaps their profession, there were no shortcuts that they could take advantage of. So for example, I went and talked to Natalie Klein, one of my favorite cellists, that I was particularly keen to ask about shortcuts, because I've spent the last few years trying to learn the cello. And I thought, no, I'd love a shortcut that could get me to play the Bach suites without having to do hours and hours of practice. And alas, she said, there aren't really shortcuts to becoming an international cellist or playing. And she had an interesting sort of reason for that, which is basically you're trying to change your body. You're trying to get a kind of muscle memory going about how your fingers run around the cello. And that actually takes time. It takes time actually to get retrain the body to be able to have that muscle memory, to be able to play those pieces. And it's a bit like she said, you couldn't become an international athlete without putting in the hours of training. You're changing your body. And so that was interesting. But she said, we do use some shortcuts. And the reason I persuade all my students to learn their scales and arpeggios is that they are great shortcuts. Because and they actually tap into one of the shortcuts I talk about in the book, which are pattern shortcuts. If you can see a pattern, that often helps you to shortcut perhaps reading the pattern into the future, or perhaps once you've seen the pattern, you don't have to read each number individually because the pattern already tells you what's going on. So she finds that that's actually the case when she's reading a piece of music for the first time. What she'll look at is see, actually that pattern is just a scale going up and down, and I know how to do that. So she won't have to read each note individually. And so she taps into a lot of these pattern shortcuts and being able to play things very quickly. She compared it actually to reading, that you don't look at every letter because you see the word. And so for her, that shortcut of the scales and arpeggios gives her a way of reading music like words rather than individual letters. Another place where shortcuts sometimes aren't possible, I talked to Susie Orbach about therapy. Are there shortcuts in therapy? My wife is actually a therapist, and she was horrified at my idea of writing a book about shortcuts, because she says, no, it takes years to actually get somebody through the traumas they might have had during childhood. And it's certainly true. There are some cases where therapy does take years, because again, you're really rewiring the brain. You're changing the brain. Susie Orbach described it, it's like unlearning English. I mean, that is very difficult. Learning a language is difficult, and I talked to somebody about trying to learn languages and shortcuts. But unlearning a language, almost impossible. So there are certain therapies that will just need time. However, you might have read about the death just recently of Beck, who came up with cognitive behavioral therapy. Not the same Beck as did the London Underground map. But cognitive behavioral therapy is an amazing shortcut in 8 weeks to be able to change perhaps behavior, to be able to cope with not descending into depression every time, but understanding the algorithm of thought and seeing that there's one point in the algorithm where if I can identify I'm there, I can take a different path and avoid deep depression. So there are some sort of therapy where you're able to rewire the brain quite quickly in just 8 weeks. The other guy you see, two guys here, are Brent Hoberman, who is a startup king. He helped set up lastminute.com, and I was intrigued, well, what was the secret to the millions you've made? His secret was breaking the law. So that was his shortcut. Now, it was interesting because actually I recognize that shortcut, because one of the best shortcuts we have had in mathematics is coming up with the square root of -1, an amazing number which enables you to do quantum physics. We use it in early radar. Complex numbers were used to land planes when using normal numbers, the planes would have crashed by the time you'd done the calculations. But that was kind of breaking a law. Before that, imaginary numbers were, every number when you square it is positive. What's the square root of -1? There isn't a number. But we broke that law and came up with this amazing shortcut. But sometimes you don't want a shortcut. And Robert Macfarlane, who's the other person in my picture here, he loves walking. He's a mountaineer. He loves taking days to get to the top of a peak. And if you offered him a helicopter to get to the top of the peak, he would say, I don't want that sort of shortcut. And I think that goes back to my idea of this praxis and proesis. Yeah, there are certain times when you don't want to shortcut the experience because the experience, the time taken is the thing. I love going walking with my family, and I remember taking our family once. We went up to the Lake District. We rented a little house, and we set off across the field on a day's walk in the hills there. And my son, I think he was about 10 at the time, suddenly he saw this little path going back across another field down to the house that we were staying in. He said, "Dad, I found a shortcut. We can get back to the house really quickly." And it made me realize, sometimes it's about going to A, but taking a long time about it. But Robert actually told me about a wonderful shortcut that he did use when he was on a mountain and the night was coming in and they had to get off the mountain very quickly, else it was not going to be safe. I learned this new word. Maybe you know this word, but he said, we were about to be benighted. It's a lovely word, so where the night is about to engulf you, to be benighted. And so he came up with this incredibly clever shortcut to get off the mountain quickly. It was snowy, and they decided to create a mini avalanche, which got them down the mountain. They just rode this avalanche down to the bottom of the mountain, and they arrived quickly at safely at the bottom. So there's a kind of exploration of other people's shortcuts there as well. The final shortcut is actually about an impossible shortcut, because it turns out that there are some problems in mathematics that we think may not have a shortcut beyond just trying every single possibility, the long way. And what I love about mathematics is it's able sometimes to turn on itself and show its limitations. Sometimes Fermat's last theorem, it showed that there are no solutions to this equation. And the classic problem that we have where we think there are no shortcuts to just the long way of trying all the different possibilities is a classic problem called the traveling salesman problem. So this is where a traveling salesman has a lot of cities they've got to visit, roads between the cities with distances on them, and the challenge is which is the path around all of the cities which is the shortest distance. So this is actually a map of the stages at Glastonbury. So I do an event in the Circus and Theatre Tent, kind of maths show there. But I always love, after doing the show, trying to go around all of the venues once and once only in the quickest way possible. And I produce this little map of the Glastonbury stages. And it's taken me some time to find the shortest path, because we believe there is no fast algorithm like the one, Euler could take a map and say, well, when is it possible actually to cross all of the bridges? You didn't need to try all the possibilities. Very clever algorithm that says, no, I just need to count the number of odd points, places with odd lines coming out. But this problem, we think that there is no way beyond trying all the possibilities. And in fact, there's a $1 million prize for anybody who can prove there is no shortcut. So this is technically called P versus NP. You actually win the $1 million if you do find a shortcut. So we don't know at the moment. There may be a shortcut, but our belief is these quality of problems that they don't have shortcuts about them. So there's a kind of challenge out there. Prove there are no shortcuts. But all of these shortcuts, as I said, the purpose of them is to get you to a point where you want to do what you want to do. And I think Gauss rather summed it up nicely in a letter that he wrote to a friend towards the end of his life. He said, when I have clarified and exhausted a subject, when I've worked out how to do everything, then I turn away from it. It doesn't become interesting anymore. He's done that. What he's excited about is in order to go into the darkness again, to look at all of those problems he hasn't found the shortcuts for, to find all the new shortcuts. And that for him was the exciting challenge of doing mathematics. Sure, he'd learned all of the old shortcuts that helped him to get to this new place where he could look into the darkness and try and find the new things out there. So I hope this evening's presentation and a copy of the book, which will be available afterwards, will be your opportunity to learn some of these amazing shortcuts that mathematicians have put together over the last 2,000 years, the kind of tunnels that we've already dug out, so you can get to the point where you too can go into the darkness and discover your own shortcuts. So thank you very much.